Hello, everybody. It's a pleasure to be here. Yet another year. Twice the room, actually. Same snake. Actually, new snake, new t-shirt. So that's a new experience for me as well. So today, my name is Luca, as I was introduced. So thank you very much, Santino, for the wonderful introduction. And by day, I work as a ML engineer in Extreme, and by night, an open source maintainer. A burden I've taken upon myself since the past year or so. So anyone here contributing to an open source project? Yeah, bunch of people in the room. Okay, good, good. How's been with the life balance, health-work balance? Okay, not so ideal, right? But how many of you here are here for forecasting, especially? That's cool, that's cool. And I kind of appreciate that not a lot of people are here because the point that I would like to make today is twofold. There are also people that will learn a bit in the next 20, 25 minutes-ish about forecasting, but what I would like to showcase here is that I cannot use a pointer. Or more precisely, that this functime library, which is experimental in a way, but could be somewhat sneakable into real production code, is built upon polars. And on its own is a bit, a living example of how polars, which I've talked about extensively last year, in case anyone was here on the last edition, can be used to build a next generation of tooling. Polars has wonderful characteristics, and this is mostly a demo of how we can use polars to envision a next generation of software, developing its capabilities and maybe allowing ourselves to experiment with the APIs. So my goal for today is to briefly introduce you to one of my domains, which is forecasting, and how it can be seen as a problem on a broader sense in terms of the whole machine learning with forecasting process on its own. And then see how functime attempts to offer a somewhat opinionated bias solution that works for the 90% of the use cases. And here they will follow up with the two ingredients that make this possible. Polars, of course, and then one of the latest trends in forecasting, which is global forecasting. And finally, I would like to endeavor myself in the really extremely dangerous field of live coding during conferences that are being live streamed. I'm not as expert as one of my colleagues, Cesare from PyCon Milano. He will be speaking tomorrow. He's an absolute god of the, actually, maybe not that, but somebody like really goes against any kind of, anything that's sacred about demos, and he'll do like 1, 2, 3 live demos at once. I will be in a much more controlled environment, but still we'll be seeing some live coding. And finally, I will do a couple of references and list different stuff. But that's the juicy stuff. And I can't say forecasting is broken. Maybe now it's a bit less popular because we're talking a lot about generative AI, but it's one of those things that's evergreen and basically anybody needs to do. But forecasting is a tedious process. It's the work of an handicraft who needs to take care of every time series, look at the residuals, fit the models. We do have libraries that offer auto-tuning for some parameters, but nevertheless, it's a demanding process that doesn't scale. It doesn't scale because if you go to 13, 14, 15 time series, then it becomes a mess to handle all of the diagnostics. And if you need to scale this to a production or a Spotify-like level, then you need to have a cluster and run a distributed system or use a Spark with MLlib or God knows what to manage all of this complexity. And to achieve what, right? That's the whole point. We can sometimes struggle to beat naive baselines, which are a fundamental aspect of forecasting. And just to achieve what, right? To deploy a model in production after months of efforts, just to achieve a 2-3%, if it works, that's the premise, but you're not guaranteed to have it work. And maybe you need to retune it frequently, right? So as Mike Gilliland said, and he's on the board of the International Institute of Forecaster and as well as a manager at SAP, he wrote a series of really interesting blog posts about where forecasting is heading, and it was a while ago. But this is actually the real point that he makes, and I think it's really interesting and tangible, and it has a really good point to make. We spend far too much time and resources about forecasting as a whole, and sometimes it's not really unlikely that we fail to achieve this goal. And so what he wants to suggest is that forecasting needs to become more efficient at a fundamental level in terms of a process rather than fitting a symmetry in a fast way. Okay? The way we can obtain gains from forecasting is not just about how we make algorithms that are faster or more precise, but how to make forecasting as a whole faster. And this is what functime wants to achieve, to make forecasting work for the reasonable scale, for the 90% of the people. For people that have a small business, for people that need to deliver production, they're not Spotify. For example, Spotify, Amazon, or whatever any other company that might have like a real advantage from working intensively on a whatever transformer-based model or whatever. And we do this and enabling the combination of the two ingredients I was talking to you about before, which are polars and global forecasting. We enable a swift and fast iterative process that allows you to forecast 1,000 of time series at once on your machine. I'm a bit biased, I have a 36 gigabyte Mac, but I think it's doable nevertheless, and it's doable, okay, without distributed systems. We also offer feature engineering and diagnostic state-of-the-art APIs to extract feature all at once from 1,000 time series at once and diagnose your whole forecaster on all of those time series at the same time. And this hopefully enables you to translate from experimentation to production. Because Polars is so slim and functime tries to be, that you can deploy it maybe on a Lambda, hopefully. And these are the two ingredients we do. So, how many of you know Polars here? Seems I've done my job, fair enough, okay. It's a wonderful library. If you haven't tried, do give it a shot. You come for the syntax, you go for the, you go there for the speed, and you stay for the syntax. It's an amazing library. It has an extending potential. I highly encourage you to try it out. But basically, it's pandas on steroids, for real. It's a multi-threaded vectorized query engine that has on top of it, a data frame library. So it's not SQL. You interact with it as a pandas object or a data frame object in Python. And it's extremely fast because it uses all core of your machine efficiently, unlike pandas, and it uses 50 plus years of research in relational databases to be extremely intelligent about the data are read and aggregated to perform an aggregation. And it is in process, a bit like SQLite, so you don't have to have like a server client infrastructure. And what can be so fast is that it enables like recent developments in the data ecosystem. For example, the Apache Arrow specification to represent data in memory. It employs Rayon, which is an extending Rust library. Oh, did I mention that Polars code is written in Rust? I forgot about that. It's blazingly fast. And it implements work stealing, which is an incredibly smart, efficient way that anybody can understand about how it processes the work all at once. I won't delve into the details, but Richie Ving, the creator, made a couple of really interesting talks and keynotes about how this works, and it's so accessible and it's so elegant that you really appreciate it. But the whole bread and butter about this is that if you do this in pandas, you will incur in some overhead, because pandas will read whole data into memory, sort the whole data set, and then return the top 5 heads. So basically, it sorted the whole row for you, the whole column for you, and then it just took the first 5 values. Polars is clever. When he sees this, he knows how to optimize this, and it just fetches sorts the top 5, and there you are. So you didn't have to go through sorting the whole row, maybe 1 million of results. Polars just does the top 5, which is a much more efficient algorithm, because only once it finds the first 5, then it's done. And then here comes the second ingredient, which is global forecasting, which is a really fancy way to say we just fit one estimator on all of the data, on the time series we have in our panel dataset or multivariate dataset. And this is a trend that's come up in a bunch of forecasting competition, as well in the recent literature in forecasting. And the bottom line is we just use gradient boosted regression trees, right? And they really perform well in forecasting competitions, the M series. How many of you have heard about it? Not many, that's okay. Basically, it's a really famous yearly competition that is held by this professor from University in Greece. The M stands for the beginning of his name, which I will not attempt to pronounce because I will butcher it inevitably. But what he basically started in the 19 or early 2000s was a competition where basically statistical, old-fashioned ARIMA methods were used. And then come like the M3 or M4 edition, where there were a lot of data into it about retail or in supermarkets and other places. And this is where the first time we had one model basically fit on the whole of the time series, coming on top in terms of performance. Really talking in terms about accuracy. But the beauty of global forecasting is that now models, especially gradient boosted trees, but linear regression as well with some clever feature engineering, can achieve a lot in terms of performance and scalability. Not in terms of, not just in terms of how fast that is, but also in terms of how fast the process in of itself is. And so here's just all that it takes to build functime. a powerful query engine to perform blazingly fast feature engineering. I forgot a crab emoji here somehow, followed by just a single method dot fit, which is an incredibly familiar API, I would say. But we took it a bit up, and by we, I mean the original creator. Now I'm the lead, basically one of the co-maintainers of the project, and the maintainer moved away. But he really envisioned a much more streamlined API compared to scikit-learn, not to demean it, of course, by any way, shape, or form, where basically we fit the model, and once you fit it, you can just call validate or conformalize and make it generate prediction intervals of your prediction using a conformal prediction, which is another framework I will talk about in PyData London later this year. And the whole point about this is you can use global forecasting models to achieve one of, I wouldn't call it state of the art, but an incredibly good model in terms of performance. But I would argue that what matters about this is that given the plethora of tools we offer to extract features from your data, and the speed that this offers, the real gain lies, once again, in the process. I think, I swear, this is the last time I'm saying that. And this is basically all the theory behind it, right? I won't go into the details, and now we can do inside the dangerous coding part, which is somehow demoed, because I have a runtime notebook, which is here. But by the way, if you go to the repository, you can also run the code about this presentation and see and run it for yourself, in case you don't trust me. We are... That's open source, right? I mean, that's just total transparency. And while I'll go a bit about that, basically what we're running here, we're just installing functime, a slightly smaller version than the one currently available on PyPI, because we're preparing for a release in the next couple of weeks, prepare for like 0.10 coming soon, which makes the promises to be stable and depend on a much more recent version of Polars, which means stability, also more compatibility, also much more speed. But just as to make an example, here we're getting some demo data, and this is basically the kind of data you're going to deal with when you work with functime. Time series data, you have a lot of one column that represents the entity, we call it, so the SKU for those in the sector, so basically the identifier of the time series. The second column represents the datetime, and the target column is the price. We just make one assumption right now, is that the data will be in this order, which might be tough. Most of the libraries, including, for example, the ever infamous Prophet, just make the assumption that you have to name columns in a certain way. We just assume about the order, but please feel free to raise an issue if you have something new in mind. Func in functime stays for functional, but I've been thinking about adding a time series dataset class. Maybe that might be a bit conflicting, but that might be one of the solutions for this. But this is how our data looks like. And this is just commodity dataset. So a bunch of observations across time, heterogeneous time zones, heterogeneous time stamps about goods that are traded at a certain price. And you can see that it is kind of unwieldy to get started with, right? Because if you need to perform exploratory data analysis, you need to start getting fancy with for loops maybe and plot a bunch of matplotlib axes altogether, and good luck with that. And what we try to do is to simply provide you convenience methods to deal with all of these time series at once. These plot entities tells you how many entities there are across all of your data set. And so you can immediately spot which time series are underrepresented, whereas which ones have more complete and homogeneous observation, like a range of observations. But you can also, at a glance, and here it's what I'm saying, I'm using a quite old version because all of this is automated and hidden under the hood of 0.95, but also 0.10. And you can display all of your time series all at once. You can just sample some of those to see at a glance how they behave. And here we see that, for example, the natural gas series in Europe behaves correctly, and then war happens. And ta-da, here we are with the prices spike. And the same goes for potassium chloride, which I think is used in fertilizers as well. The sunflower oil, because Ukraine was producing, and is one of the biggest producers in the world, etc., etc. And this is hard to deal with because here this is a really naive data set, but still it really displays a change point, no air passenger states, where you will just have a really predictable trend and seasonality. And this is real world data. But what we can do and what we offer, which here is just written plainly, out in code, but from the next release will be just under the hood hidden for you. You can just define a metric. See here, for example, we can just use one of those metrics named coefficient of variation, which is basically the ratio between the standard deviation and the mean, and compute it for every time series. And now we have a way to sort all of our time series and display them by that error metric or metric that we choose to display them on with. We have a bunch of those. Here I'm just randomly playing out. But still, for example, here they are the series that basically have the ratio of the standard deviation towards the mean that is biggest. And here we see that actually these series that behave well are coal, crude oil, actually the worst, crude, and for example gold. Of course, we know it. There's been COVID, and then there's been war. So the price has been the behavior of the market has been crazy, and we try to hedge and invest in securities and refuge goods. And sea phosphate rock, that's another one I was mentioning before. So we have a way to start to, and we want to offer an API that enables the user to glance over a multitude of time series at once, well beyond the just inspect and inspect the residuals or decompose all the time series into trend, seasonality, and residuals. We will start to give an approach to make the exploration scalable. And then here we are with the scikit-learn familiar API to transition from experimentation from exploration to experimentation. We do have, here is where we try to mix and match a bit of functional programming with the old familiar API. So basically this is, it's basically a decorator, but it's basically a function that returns a function. This is like a curried function if you want to name it in a fancy way. And there's going to be another incredible talk about functional programming in Python. I think it's today in a couple of slots, so make sure to go check that out. And here basically we just build a train test splitter as we were doing functime. And the beauty of this method is that we abstract away the complexity to perform these operations on all of the time series at once. So here you specify the forecasting horizon, so how many observations you want to keep aside for the final test. And you see here that basically, if you inspect the test set, we did the separation in train and test split all under the hood. So you didn't have to write, for example, a for loop or do the group by of your own. And if you use pandas, they will start to get slow and slow. And then we have and implement a plethora of benchmarking methods. The seasonal naive, for example, we specify a frequency. We say of the forecast, the future forecasting horizon, the frequency of the observation, and the seasonal periodicity. And we can just call method. We define the forecaster. We just call forecaster.fit, forecaster.predict, usual standard scikit-learn API. But still, you see that the predictions are generated for all the time series at once. So when you do inspect the prediction, you will see them properly arranged according to the time series. And it was computed for every one of those. Here, it's kind of a bit cheating somehow, because of course, when we do to the modeling part, we just do one model on the whole time series, but prediction needs to be generated for every one of those separately. So we do them for you. And if you look at diagnostics, we just have a plotting method, a plotting submodule with plot forecasts, for example, which we can use to plot a sample of K forecasts, of K series. And here we see our naive method and how it behaves compared to natural gas. Here I'm using, here I'm not using a metric, but we can sort, we can just import from the evaluation module, the rank point forecast function, and use it to sort all of the prediction that we made. Using here, I don't like using mean absolute percentage error. Don't use that in production. Don't use that maybe period, especially if you know that your data is going to get closer and closer to zero, because if being a percentage, being a ratio, it will explode. So don't use this. This is here just for educational purposes. You never know. We can rank the forecast and see which model have the highest and or lowest error. And we can use those to basically display the prediction by the worst, like display the models and see on what series it went from best or worst according to a certain metric. So for example, here we can see that our naive model didn't perform fairly well on potassium chloride, urea, coconut oil, and palm kernel oil, and natural gas as well. Of course, being a seasonal mean, we expect it to underperform when there is a change point, right? Given that also we set like a breakpoint of like a periodicity of 12, which means 1 year on the data that we have. And now we enter with the modeling side, right? And we can always use the good old linear models, because if we pair them with clever feature engineering and we re-implemented the whole of TS-Fresh, which is a famous feature extraction library for time series, re-implemented everything in polars, plus wrote some Rust custom kernels to make it run even faster, you can have and explore a plethora of feature extraction method to extract signal from your features. And we tried to be a bit more on the experimental side with this and offer a novel take on the API. So instead of building a pipeline that looks like a scikit-learn pipeline with feature unions, with column transformers, we just accept a list, of an argument parameter. You don't need to write logic to make the shifts. We will do them for you for every series. And basically 2 other arguments that accept a sequence of objects, or just a plain object, of the target transformation, so the transformation that you want to apply to your Y, and then the feature transform, which are the features that you want to extract. So here, for example, I'm fitting a linear model that has basically computes the mean and standard deviation as actually the rolling mean and standard deviation over a window of 6, 12, and 24. So basically, I'm computing a standard mean with a window of 6, of 12, and 24. And then we can use those using all of the methods that polars implements, including, for example, the exponentially weighted average. And this is good. We just called model.fit, model.predict. Here I'm just using a bunch of the dictionary option because we can just call .backtest to perform automatic backtesting. So cross-validation, but for time series forecasting. And we can plot the backtest, and this looks like a bit, I'm just sparkling a bunch of coriander on top, but I swear that if you zoom in, and I think if my browser allows it, then we can see that basically it's just 5 different prediction plotted all alongside one of each other. And of course, we can do all the function and ranking residual, but what I really like about functime, what made me fall in love with it and starting to become a contributor, is the plethora of diagnostics plots that we can have to see at a high level how this performs. And here, I really like this rank residuals combined to plot residual function to display, for example, the residual of the forecaster. And here we see basically how they are stacked together in a distribution to display which time series behaves best or worst in this case. And here, for example, we're looking at the baddies, actually the best ones, and see that we have our estimator is not really normal in the distribution of errors. Some series are more compressed than others, and it really is really tall in terms of a normal distribution. And this is somewhat okay, and we can kind of do the same with some tree methods and see that you see that the 3000 here top, this is a bit more smaller, so it's a bit fattier on the side. But what we can really do is have a plethora of tools to compare against a bunch of models together, the performance. And this is one of the plots that I really like and I would really love to talk about. I don't really remember the name about this, but basically it's just this plot is, it's called a forecast value added. So it tells you the value that a forecaster adds compared to a baseline. So here, for example, we plot the predictions of the light gradient booster, so gradient boosting trees, and then we perform against the benchmark, which are our naive forecast. And on the x-axis, we have the naive forecast, and on the y-axis, we have the light gradient boosted machine. The straight line represents basically the equality. So on the x-axis, you have the error over every time series according to the naive model. And then on the y-axis, you have the error according to the light gradient boosted machine. If the 2 models were the same, we would see them basically aligned along this straight line. And here it's kind of what we see, right? That the benchmark and the forecast error with this map, unfortunately, but still, with a light gradient boosted machine are kind of the same. And so here we can immediately inspect the outliers. So which function behaving oddly or have the highest error compared to a baseline and see if our models are actually more capable than just a baseline. And we can do the same, and we can, of course, compare, and this is extraordinary. If we do just the linear regression against the seasonal naive, we see that the naive model performs really well, because if the points are below the diagonal line, we see that the model below here is better for those time series. So here we overperform with a naive model. Actually, our linear forecaster underperformed compared to the baseline. And we have another similar one, which basically plots one of the error metrics, the coefficient of variation, for example, on the x-axis against the error of our choice, in this case, the symmetrical mean absolute percentage error, don't use this, for the light GBM boost. And here we see that in this quadrant, we have points where a time series where the error is low and the coefficient of variation is low, good. But here we have a low error in terms of coefficient of variation, low variation, but high error. And so this immediately tells us which time series require more attention. And this is the kind of tools that we would like to offer to make your process of forecasting faster. So the point that I was trying to make was to make the process faster, right? To identify the critical series, provide you a series of tools to just fit one model and see where it doesn't behave really well. Add some more, and then you can customize your feature extraction, which is demonstrated to be empirical, but also in papers and competition, to be the key value to enhance your forecasting models. And so in this way, for example, we would like to offer you tools to see all those time series at once, fit just a naive model, and see where it belongs, and then iteratively see how you can make it work for the whole of your data up to a reasonable level. But here you will see, for example, that liquefied natural gas behaves unwieldily, and then you can customize your feature engineering to, for the purpose to better fit on that data. And I think that basically this is it. Just to give you a vibe about it, of course. And this is a really great feature, and then we have so many more of them. For example, hyperparameter tuning, sensor forecast, and also like a just OpenAI call to analyze the data, whatever. This is just a market at this point. Even terminal applications now have those, and I'm not joking. If you want to read more about it, there are a bunch of references of talks that have been given across the past year. The Discord and Polar's documentation is really welcoming. We try to be too, so please opt in if you really want to. And for that works, I would love to thank you for your attention, and I'm really eager for your feedback about how this project is shaping, about I gave this talk, so do not hesitate to reach out. I would love to make this project even better and to hear you about how I can make it better and make it custom tailored for your use cases. Thank you very much.
Thank you, Luca. So there is some questions that were in the, there is a Slido up for the next.
Hi, it's a fantastic talk, first of all. I have one question about the generalized model, because I would really like to know how the information is shared between the different commodities. When you talk about the linear model, I assume that obviously you scale differently each of the commodities, and also when I think of a linear model, I think that maybe there is a categorical feature that encodes the entity, but this is not sharing information because there is no parameter sharing at that stage, I would say, or really little. So I would really like to know about this. And the other question is, how do you deal with the exogenous variables, if there are any? Would this approach work with exogenous variable also?
So starting from the last question, which is how we do support exogenous features. You can pass them as an argument to the .fit and .backtest and whatever methods we do. Going to the first question, yes, basically just one model that is fit on the whole of the thing. Some of the identities, for example, the SKUs or the identity, are treated as categorical features. If you do extraction of features from the date times, for example, you extract the month of the day, the month of the year, it will be treated as I don't remember for sure if it defaults to one not encoded. It might be treated as an ordinal. That's because maybe linear models in this case don't really perform well, but gradient boosted trees understand those kind of features. You were saying that there might be some not information being shared.
Yeah, how do you have an advantage for having a global model rather than having a single model for each commodity? So how is this information shared?
Since it's just one model, just have one set of parameters. So it knows that they can treat one of the SKUs, for example, as an ordinal feature. So it switches, they're just going this way, the bias using that information encoded in the categorical values of the SKU or the entity column.
But do you think that, for example, a linear model would benefit for a global model, or the linear model?
The linear model, maybe not.
Yeah.
That's maybe not maybe likely to underperform, because if you have many features and you fit a linear model, we know that ordinal encoding doesn't really work very well. So if you need to just use one-hot encoding, then you will have too many dimensions. It will become sparse. But gradient boosted trees handle this very well.
Okay, thanks.
You're welcome.
Yeah, I will have more questions for later.
Okay. Therefore, the last one.
Thanks for a very beautiful talk. One question, do you know the project SKTime, and do you take inspiration or collaboration with them?
So Christopher, the creator, was once a contributor to SK Time. I was dabbling with it back when I started into forecasting. We didn't talk very much. We should try to cooperate. The point is that we have different goals, and they try to be extremely compatible with the scikit ecosystem and provide anomaly detection and a bunch of other features, while on the other side, we just be more tailored to forecasting with polars especially. So if you just, basically this means if you have a pandas data frame converted to polars, then it works with us. We don't do that for you.
Okay. Thank you, Luca.
Thank you very much.